Minail, I think, has connection issues. One sec. I said we last time we were almost done with lattice energy, okay? So we were done with this, and we had done electron affinity as well. So we were supposed to start with we're going to start with Born-Haber cycle. Okay, that's basically a Hess cycle. Okay, so you've got your Born-Haber cycle, which is basically just a Hess cycle. And this Born-Haber cycle was specifically used for calculating lattice energy, because last time we had discussed that lattice energy, it's very hard to calculate lattice energy directly. So specifically, it's used to calculate the lattice energy of different substances. Okay, so what is the Hess law? Hess law states that the enthalpy change of a reaction is the same no matter what path is taken. ठीक है, तो एक सेकेंड होल्ड करो. Zaina, you've joined the class, right? Yeah, you there.
Yes, sir. Thank you.
Okay. I said, so what was the Hess law? Enthalpy of reaction is the same. Is the same no matter what path is taken. So no matter what path you take, as long as you make the exact same substance. Okay, that was what the Hess cycle or the Hess law was. So for example, I'll just give you an example that if carbon reacts with oxygen and it ends up producing carbon dioxide, and this reaction has a certain enthalpy change, let's call that delta H1. So there are a couple of ways you could have an alternate path. Okay, your starting point is this one, and you want to reach the other side, which is carbon dioxide. So there's an alternate path as well, which is that what you can do is you can first make carbon monoxide, and then once that carbon monoxide is formed, you react it with half O2 gas molecules, and you'll end up with carbon dioxide. So there's an alternate path which could have been taken. That alternate path requires two reactions. So there's enthalpy change 2 for reaction number 2, where you convert the carbon to carbon monoxide first. And once that happens, the carbon monoxide then reacts with oxygen again, and that's a third reaction. You call it delta H3. So what was Hess law? Hess law was one path is equal to the other path. So that means this path, the direct path, is equal to the indirect path. So that means delta H1 is basically equal to delta H2 plus delta H3. So all three reactions are kind of interlinked. And if you know two reactions and you don't know the third enthalpy change, then you can obviously find the third enthalpy change. So what needs to be understood is that your starting and end point, once a Hess cycle is drawn, your starting point and your end point can be, you can choose any starting point, any end point. So for example, if this is my path 1, then the other path will be going all the way from the other side, right? As long as your starting point and your end point is the same. So these two paths are also equal. So that means this path over here is delta H3. And this other path is, because I'm going in the reverse direction, so delta H2 will be minus delta H2. तो ये वाला जो पाथ है ना, this one over here, the one that I'm highlighting, ठीक है? So it's going to be minus delta H2 plus delta H1. So there are many ways of manipulating the Hess cycle once it's made. You can select any two paths as long as the starting point and the end point is the same. The two paths will have the same enthalpy change. And these two are exactly the same equations. Okay? They are rearranged versions of each other. So it's not a different equation. Okay? This is exactly the same. So is this clear, Hess cycle? Is this clear? You clear this, Arafo?
Yes, sir.
So moving on, what's the Born-Haber cycle? The Born-Haber cycle is specifically for calculating the lattice energy. Okay, so what was the lattice energy? The lattice energy was, I said, normally what you do is, normally the Born-Haber cycle starts with enthalpy of formation. And remember, it's for ionic compounds only. Lattice energy is it's specifically for ionic compounds. So normally Born-Haber cycles are all constructed in kind of exactly the same way. So for example, I want to construct the Born-Haber cycle for magnesium oxide. I want to figure out the lattice energy for magnesium oxide. The way I'm going to do this is there is normally you have an energy axis. They normally give you an energy axis in the question. Now, to construct the cycle, it's done this way, that you start off with enthalpy of formation of magnesium oxide. That's the first thing. What is enthalpy of formation? Enthalpy of formation is that you form magnesium oxide from its elements. The elements are magnesium and oxygen. Magnesium is a solid, it's metallic, and oxygen is a gas. And using these two, you form magnesium oxide, which is the ionic lattice, and that's a solid. So the enthalpy change of this reaction is going to be called the enthalpy of formation. And to balance this out, there's going to be half O2 gas. So the cycle starts, normally it's easier to make the cycle using enthalpy of formation. So that's your starting point. And you're going to try and find another path that will form magnesium oxide. So you're going to try and do this stepwise. How could you find another path? And then you'll make a Hess cycle, okay? So how do you create this other path? So what you're going to do is, okay, before making it over here, I'm gonna do this over here, like a simple Hess cycle. Then I'm going to construct it with the energy axis. So basically, I've got these elements. And I want to form magnesium oxide solid. This is my enthalpy of formation. Now my starting point is elements. Okay, there's magnesium solid and there's oxygen gas. And I somehow have to form this ionic lattice, which is over here. So there are two things that I'm going to do. The first thing is I'm going to break the bonds in the element, right? Magnesium is metallic and the oxygen molecules are all bonded to each other. So the first thing I'm going to do is I'm going to atomize. That's the first thing. So I'm going to break the metallic bonds and I'm going to get magnesium gaseous atoms. And I'm going to break the oxygen gas molecules. And I'm going to get oxygen gaseous atoms. That's the first thing. Okay, the first step is you atomize. And once you've atomized, because I want to form magnesium oxide, I'm going to ionize them. So the next step is I need to ionize them. I need magnesium to convert into 2+ ions, gaseous, and I want oxygen to convert into 2- gaseous ions. Once I've done that, the ions will get together and they'll form the ionic lattice. So when gaseous ions form the ionic lattice, that's known as the lattice enthalpy or lattice energy. So every time the Born-Haber cycle kind of looks like this. There are two steps. Enthalpy formation, you've got elements and you want to form magnesium oxide from it. So the elements have to be atomized and then they have to be ionized. And once they formed ions, then you form the ionic lattice, and that's your lattice enthalpy. Is this part clear? Okay, this is the rough Born-Haber cycle. Is this clear?
Yes.
Yes.
Achha, so we're going to do the same thing, but over here in a lot more detail. Okay, so I want to start off, and remember when you have an energy axis, endothermic means you're going up. If something is endothermic, so that indicates that the direction of the arrow goes up. And if something is exothermic, then obviously the direction of the arrow is going to go in the downward direction. So if the arrow is going downwards, that means it's exo. So remember the same cycle that I've drawn on the right side, I'm going to draw it over here, but with the energy axis. So the first thing is I'm going to atomize magnesium and oxygen, but I'm going to do it stepwise. So first thing is I'm going to atomize magnesium. So this will be enthalpy change of atomization of, it's going to be enthalpy change of atomization of Mg. So delta H atomization of Mg. So Mg turns into gaseous atoms. And I don't do anything to oxygen. So the half O2 remains as it is. Nothing happens to it. Next step, I've only atomized Mg yet at this point. I'm going to atomize oxygen now in the next step. So oxygen is going to get atomized. So oxygen will be, I'm going to make another arrow. So why is the arrow going up? Because atomization involves bond breaking and it is endothermic. So magnesium is already atomized, it's gaseous. Now the oxygen bond has been broken and it has also turned into oxygen gas. So this is enthalpy change of atomization of oxygen, which is basically equal to the bond energy of oxygen. It's half times the bond energy of O double bond O. Because remember it's a gaseous molecule, so you're just breaking the bond of oxygen. So this completes the first step, which is that I've atomized my atoms, elements. Next step is I'm going to ionize them. Now, ionization of magnesium is endothermic as well. So the arrow would go up again. So it's going to go up once more. I'm going to choose a different color 1 second. That's just the arrow still goes up. Wrong direction, 1 second. So Mg is supposed to lose 2 electrons. It will become 2 plus. It lost 2 electrons. The oxygen isn't really doing anything yet. Mg was gaseous. The oxygen hasn't gained electrons. So this is the first plus second ionization energy of Mg. So it's the first plus second ionization energy of Mg. Now the next step is I need to ionize oxygen. That will be the electron affinity. So I need to ionize oxygen. So Mg has already lost electrons. Mg2 plus is gaseous. Now oxygen is supposed to gain 2 electrons. That's going to be 2 minus, and that's also. Now it has turned into ions. This step over here will be the electron affinity of oxygen plus the electron affinity of oxygen minus 1. It's gaining 2 electrons. So it's the electron affinity of oxygen plus the electron affinity of oxygen minus 1. Now, I'm pretty sure about atomization being endothermic. I'm also sure that the ionization energy is endothermic, so the arrow is going up. But this part is tricky, which is that electron affinity. Remember when we talked about electron affinity, where the atom gains electrons, we had discussed where's electron affinity? That was the last thing we did. So in electron affinity, I told you that the first electron affinity is exothermic, so the arrow should go downwards, while the second electron affinity is endothermic. So in the case of oxygen, I'm actually making it gain 2 electrons. So I'm not really sure what the electron affinity is because the first one is endo, the second one is exo. So together, whether it's endo or exo, I'm not really sure. So I can just Google it for now. So electron affinity of oxygen atom, ठीक है? So electron affinity of oxygen is uh what's the total electron affinity? Oxygen minus 2 ion. ठीक है, not really sure if but let me look at it in a worksheet just a second. Lattice energy, just a second, this one. So somewhere there must be given the electron affinities of oxygen, ठीक है? Because we're not sure whether it's endo or exo. So this is given over here. So you can see that the electron affinity of oxygen, the first one is exothermic, but the second one is highly endothermic. So overall, if you sum this up, this is overall it's going to be endothermic, which means the arrow direction will be upwards. So which I've done over here as well. ठीक है, you can see the arrow is still going upwards. So we're kind of done with half the cycle, which we had discussed. ठीक है, we started off with enthalpy of formation over here at the bottom. The elements were atomized. Magnesium was atomized. Oxygen was atomized. Then they were ionized. Magnesium was made to lose the first 2 electrons, first plus second ionization energy of magnesium. Oxygen was made to gain 2 electrons. That was the electron affinity of oxygen and oxygen minus 1. So the arrow was still going up. I mean, this is still higher up. And finally, I have gaseous ions. So finally, what's going to happen is that the gaseous ions are going to get together and they are going to form the ionic lattice over here. So that's going to be my lattice energy. And that's my Born-Haber cycle. So every time it's going to follow these 3 things. You're going to atomize, you're going to ionize, and then you're going to form the lattice. They'll give you values for everything, except for most of the time, they're not going to give you the lattice energy, and you're supposed to calculate the lattice energy. So your lattice energy in this particular case, what is it going to be? It's going to be one path is equal to the other path. So that's your one path. The other path is you're going to go all the way in the other direction. So you're going to go all the way in this direction. That's your other path. So if I write down the expression, it's going to be a pretty long expression. So my lattice energy would be all these signs are going to change direction. So it's going to be minus electron affinity of oxygen and minus the electron affinity of oxygen minus 1. The first plus second ionization energy is also going to change direction. So it's going to be minus the first plus second ionization energy of magnesium. And then it will be minus the enthalpy of atomization of oxygen. And then it will be minus enthalpy of atomization of magnesium. And then it's going to be plus delta HF. The delta HF arrow is in the right direction, so you don't need to change the sign of that. So this is going to be your lattice energy, and you'll solve for this expression. The values for the rest would be given to you, and you're going to find what the lattice energy is. ठीक है? Is this clear? ये clear? Zaina, is this clear? Jody, is this clear? Meher, clear है?
Yes, sir.
So it's all about practice, right? The only thing you have to be very careful about is that there's a lot of addition and there's going to be a lot of subtraction. So you have to be very careful with the signs. You have to be careful on your calculator. Sometimes the values will be multiplied by half. Sometimes they'll be multiplied by 2. So we're going to just practice this worksheet, TK, which is over here, and try and do these questions. So for example, so all questions would kind of be similar. So for example, I've got potassium oxide over here. They're asking for the lattice energy of potassium oxide, right? So you're going to just start the same way, which is you're going to start with enthalpy of formation. Although there's no energy access given, but you should, I mean, sometimes they're going to give you the energy access as well. So we're going to just start with the energy access anyways. So the elements, which is potassium solid, plus what's the other element? Oxygen gas. Together they are forming potassium oxide. So that's my enthalpy of formation. That's delta HF. So I'm going to find the other path, which is all the way stepwise, right? So I can, since they're not really looking for the complete diagram, so I'll just do everything in one step. You're going to atomize. So potassium needs to be, remember, it has to be balanced. There's going to be 2 potassiums, and there's going to be half O2. So 2 potassiums and half O2 gas molecules. Okay, you have to be very careful with the moles. So potassium has to be atomized and oxygen has to be atomized. I'm just going to do it in one step. So 2 potassiums turning into gaseous ions and the oxygen gas molecule also turning into gaseous atoms. Now the atomization of potassium is given over here. That's plus 89. So this is plus 89 and times 2 because I'm doing it for 2 potassiums. Now, oxygen's atomization is not given. It's basically, what are you doing? You're breaking half moles of oxygen-oxygen double bonds, right? That value can be found in the data booklet. Now it's going to be printed next to the question, but if you look at the data booklet, the bond energy of oxygen is given, which is somewhere, where is oxygen? This one. It's given as 496. That's already given to you. So you're breaking 496 times half moles of oxygen, double bond oxygen are being broken over here. So this is atomization. I've atomized it. And the next step is I'm going to ionize them in the same step, like together. I'm going to just ionize them. So I need to form 2 potassium ions and I need to form oxygen 2 minus ions, gaseous. So in a single step. So what does that require? That requires, so what does that require? That requires ionizing potassium. Now, again, that's not given over here, but that's given in the data booklet. If on a certain page, TK, this one, I think, the ionization of potassium is given. TK potassium is proton number 19. If you want to ionize potassium, that's 418. TK, your top likha, first, second, third, fourth ionization energies. So if you want to ionize potassium, that's given, it's 418, right? So that means for this, you would require 418 kilojoules of energy. But since there are 2 potassiums, I'm going to multiply it by 2. And I also need to turn oxygen into oxygen 2 minus. That is given over here. That's minus 141 and plus 798. So I've turned it into ions, and the last step is I'm going to form the ionic lattice, and that's my lattice energy. So one path is equal to the other path. So my lattice energy is now basically equal to all of this. So my lattice energy is equal to the other path, which is so the signs of the arrows, the direction of the arrows has to reverse. So it's going to be minus 2 times 418 plus 141 minus 798, and then it's minus 89 times 2. I said somebody should start solving it on the calculator. Then it's minus 496 times half. And then it's enthalpy of formation, which is also given. That's minus 361. So minus 361. So that's what my lattice energy would be equal to. तो क्या आ रहा है? Has anyone tried this?
I'm still typing it in.
Okay.
I got minus 2,280.
ठीक है. So minus 2,280, which is fine. ठीक है. That's kilojoules. But remember, for this, you would have to be very careful with the moles that are involved. For example, over here, there were 2 potassiums involved, so you have to multiply everything that's related to potassium by 2. So that's the correct answer. Okay. Now, the next part, let's do another question related to. So for over here, they've constructed the Born-Haber cycle for sodium oxide. So can you tell me what? And they've asked you to label all of this, right? A, B, and 1, 2, 3, 4. All of this, they're asking questions about it. So can you tell me what this arrow 4 is? Or what name would be given to this?
Delta H of formation.
Okay, that's delta HF formation. Elements turning into 1 mole of compound, right? Now over here, so the first step, they're going to atomize, then ionize, and they're going to form the lattice, right? So atomization, what is A then?
Sodium gaseous.
Okay, so that's sodium gaseous. Okay, so sodium gas. Acha, what is 1?
Delta H of atomization of sodium. 2, actually.
The sodium is already atomized over here.
Ionization energy of sodium.
Okay, what is happening?
First
how
one.
how first ionization energy? What is happening over here? Nothing is happening to oxygen. Sodium is turning into ions, right? So that's the first ionization energy of Na, and times 2, because you're doing it for 2 sodiums. Okay, Zaina, is this clear?
Yes, sir.
So the next one, enthalpy of atomization of oxygen. So what is B then? क्या होगा जोड़ी? Any idea, Meher?
Oh, gaseous?
It's just going to be that you're atomizing oxygen, so you're breaking the oxygen-oxygen bonds, and it will give you oxygen gaseous atoms. That's it. And over here, what is happening in this path over here? It's
Sir, doesn't half O2 mean the same?
क्या चीज?
Matlab, isn't it already half O2? So isn't that already atoms?
नहीं, half O2 means half moles of oxygen gas molecules. This half over here doesn't mean that it's literally being halved, right? Half means half is a very big number. It's half moles actually. Half moles किसके equal होता है? That's equal to 6.02. What's the half of that? 3.01 times 10 power 23, right? That's a lot of oxygen molecules. वो clear है?
Right, sorry, I thought too.
ठीक है. So the half moles is like a huge number, okay? So when you break the bonds of half moles of O2 gas molecules, you're going to get 1 mole of oxygen gas. As the next one, what's this? It's oxygen gas turning into oxygen minus 2 ions.
First and second ionization energy of oxygen.
No, but you don't call it ionization energy, you call it electron affinity, right? Which is the same thing, but they're gaining electrons. Is that clear?
Yes, sir.
So it's the electron affinity of oxygen and electron affinity of oxygen minus 1. Once you have gaseous ions and you're forming the ionic lattice, what is 3 then? Well, what is 3?
The lattice energy of sodium oxide.
Yeah, that's the lattice energy. Okay, that's sure. So I think in this question, they were just asking you to label everything, right? So I think in the next part, they're asking for use your cycle, the following data and further data from the data booklet to calculate a value for the lattice energy of sodium oxide. So we're going to try and do this. Enthalpy of formation is given, that's minus 414. So I'm just going to plug in values. So this is minus 414. So what else? I think enthalpy of atomization of Na is also given. That's the first one. That's 107. So I'm going to plug that value in. So that's 2 times 107. Now the first ionization energy of sodium is not given. That's given in the data booklet. So the first ionization energy of sodium is 11. Okay, so it's given as its value is 494. So we're going to use that 494. So this is 494 times 2, the first ionization energy of sodium. Now, did they give us the enthalpy of atomization of oxygen? That's they told us that the atomization of oxygen is basically equal to half the bond energy of O2. That's what they told us. So we're going to look at the data booklet and we're going to find the bond energy which is over here. That's given as 496. Okay, so that's 496. So this one is 496 divided by 2, right? Because you're breaking half moles of oxygen molecules, right? The electron affinities are given. And so what are the electron affinities? That's the first electron affinity is minus 141. The second one is 798. So that value is given. So minus 141 and 7. Again, be very careful with the moles in the equation. Anyways, lattice energy. How do you find lattice energy? One path is equal to the other path. So that's the other path. So the arrows have to go in the opposite direction. So your lattice enthalpy would be plus 141, minus 798, and then further downwards, minus 496 times divide by 2. Then it's going to be minus 494 times 2. Then it's going to be minus 2 times 107. And then it's plus delta HF, which is minus 414. So this entire thing, okay, your lattice energy is equal to this entire thing. So what do you get?
Minus 2,521.
Okay, so you're getting delta H is equal to minus 2000. Let's we confirm, let's double check whether that's the right. I mean, I'll open the marking scheme. Because the thing is, even if you do everything right, you might make a mistake on your calculator. So you have to be very careful with the answer. So this second one is, this one, right? Yeah, it's minus 25. That's minus 2521. Okay, and we can do one more. 1 second. That's again sodium oxide, so that's like a repeating question, so we're gonna skip that. Yeah, over here they've actually indicated that you have to complete a fully labeled Born-Haber cycle. So now you have to like in the previous case, I just atomized it one step and I ionized everything in one step. Now I have to draw a fully labeled Born-Haber cycle. So first thing, calcium is atomized and nothing happens to Cl2. So Cl2 is gas. So that's step number one. And I'm going to label it. That's enthalpy of atomization of calcium. Then Cl is atomized. Atomizing Cl means that I'm just breaking its bonds. So Ca is gaseous. And now I've got two Cl gaseous atoms. So that's the enthalpy of atomization of Cl, but multiplied by 2 because in the enthalpy of atomization, you form one Cl atom, right? Now I'm forming actually two Cl atoms. So this is enthalpy of atomization of Cl, but multiplied by 2. And this thing is equal to the bond energy of ClCl. Then I'm going to ionize this. So I'm going to ionize calcium first. Calcium will form 2+ ions and it's going to lose 2 electrons while Cl is not doing anything at the moment. Okay, I need to write down the states. Calcium was gaseous and the Cl is also gaseous. So what is this? This is the first plus second ionization energy of Ca. Okay, fully labeled. Then the Cl is supposed to gain electrons. That thing, I think, the first electron affinity, I think, is exothermic. Or you can have a look over there as well because we can't mess up the arrows, right? Cl's electron affinity, that's given, that's -349. So that means the arrow is going down from here. So the Ca was gaining, had already lost 2 electrons. Now the Cl is gaining electrons. Okay, remember, the electron affinity of Cl is given as exothermic. So that's why my arrow is now going downwards. So this is electron affinity of Cl times 2. And finally, the gaseous ions are forming they're forming the lattice, right? So that's your lattice energy. And again, it's if you want to solve this is 2 marks for the complete labeled Born-Haber cycle. So the lattice energy is equal to the other path, which is this entire path. So all the arrows have to change direction and you're going to solve for it. TK, is this clear? This one?
Yes, sir.
So just last one, try solving this one because they're going to ask you for the answer. So your lattice energy is now in this case equal to, everything is reversing. So electron affinity of Cl times 2. So that's plus 349 times 2. The first plus second ionization energy of calcium that can be found from the data booklet, which is with calcium. So calcium is over here. That's 590 and 1150, these two. The first plus second. So since the arrow is reversing, it's going to be minus 590 and minus 1150. Then it's the enthalpy of atomization of Cl. And the arrow is reversing. So enthalpy of atomization of Cl, that's equal to the bond energy of ClCl. So again, I have to look at the data booklet. The Cl-Cl bond, right? That's 242. So this one would be, again, minus 242 because I'm going in the opposite direction. So remember, I'm not going to multiply it by 2. The bond energy, because if you break one Cl-Cl bond, you get 2 Cl atoms, right? So I'm not going to multiply it by 2. I just need to break one bond over here. And the calcium is atomizing now. Calcium atomization is 178, but the arrow is in the other direction, so it's going to be minus 178. And finally, you have the enthalpy of formation, which is minus 796. Okay, is this clear? And what is the answer that you're getting?
Minus 2,258.
Okay. So just this one, remember that specifically this one. I was only breaking ClCl, I was only breaking one bond. So that was only 242, right? So we got 2258. So okay, we'll continue next time. We'll do a few more questions. We're pretty much done with Born-Haber cycle. So I'm going to share the worksheet as well. So you can try and practice these questions. And next class, we'll probably move on. We'll do a few more questions, then we'll move on from this, okay? So let's continue next time then, on Monday. Okay? And okay, then take care.
Okay, sir.
Hafiz.
Lattice.
Thank you, sir.